I'm Kris, and welcome to a practical guide to loose coupling, a talk I bet all of you were waiting for because it's about software engineering and not about just coding. So I know that there were a lot of talks about coding, great talks. Everyone likes that. I love that. I love talks about template metaprogramming. I'm working for a high-frequency trading company, so I apply a lot of those techniques on in my daily job. However, this talk is not about that. It's actually about higher abstractions, which are important, and the goal is to actually improve the quality of the code around the globe. So yeah, without further ado, let's dig in and see whether we can actually achieve that. So hopefully, I know it's late, I know it's hot, but hopefully you'll be able to push through and you'll be as excited at the end and learn something as I am right now. I would like this talk to be interactive if that's possible. If you have any questions or doubts or you want to destroy any of the practices, I will try to point out. Feel free. I'll try and take it and hopefully I will be able to find maybe even better solutions to problems which will be described. All this talk is based on C++, as you can imagine. There will be a lot of coding examples and hopefully we'll be able to have some fun with it. So let's move on. How we'll go about it? Because it's not an easy talk. It's not a talk about this really cool trick in the compiler or a coding technique which I just learned. It's about how to approach software engineering. So a lot of us are programmers, coders, but the step above that is being able to be a software engineer where we write the code not just for us, for our stakeholders, we write it for everyone, for our team, so that in 10 years' time, wherever someone will look at this code, they will understand why it was written like that, and everyone will be, proud of what has been written, and that's the way we should approach software engineering. So that's the motivation. I hope that sounds good. Obviously, we'll take a look deeply into loose coupling code, because loose coupling is, I think, the very underestimated technique when writing software, and it's really important to apply it correctly so that the code will be high quality. A lot of talk will be related to object-oriented design. However, not everything. Object-oriented design is often used in software engineering because there are a lot of background techniques about that. But there will be techniques as well for functional programming, for other techniques. Not really for the procedural part because that's kind of hard to do. We'll take a look into single responsibility. We'll take a look into dependency inversion, dependency injection, why we apply those techniques to get loosely coupled code. One of techniques which is really important and not very often applied, it's Law of Demeter. This principle will be important in that talk. And obviously we'll summarize at the end. As I pointed out, there'll be a lot of slides with code examples, but sometimes some of them will have the dark blue background, and those slides I consider very important and something to learn. So since the goal is to get the quality of the code around the globe to improve, the blue background slides definitely will try to achieve that. So I don't know, I can't really ask the audience, but if we're in person, I would ask who know Uncle Bob or Bob Martin. I would assume everyone, because everyone in this conversation here with me care about quality software. And Uncle Bob, Robert Martin, also cares about it. So Clean Code is one of my favorite books. It's related to object-oriented programming, but it's really good about how to actually write software and what is important. So if you have the skills by applying code techniques, we know the syntax, we know the language very well, the step above will be to apply techniques to write the software for everyone. And my favorite book, I actually have it here as well in paper, Pragmatic Programmer. If you haven't read it, I really encourage everyone, because even in this talk, we'll quote a lot of things from that book. It's personally my favorite book all time about software engineering. And the quote, notice here the blue background from it, from that book actually, the essence of good design. What that means? That the good design is easier to change than the bad design, etc. So this talk will be all about that. Loosely coupled code is about that. Why? Because, for example, good naming is important, because if you have good names, it will be easier to understand the code. The code is 90 times more often read than written. So that will give us the better ability to easily change it, because we will understand it. So good design is easier to change. If you have, dependency injection patterns, when we, separate concerns from the business logic creation, that's also important, because that will eventually give us the ability to change the code easier in the future, which means that it's easier to change, which makes the design better. So I wanted to point out that it's really important throughout this talk, and all the techniques and everything is always applied through that. It's not often seen up front. Sometimes we make decisions based on the circumstances we have, and we may go far as a mistake in the design. In that case, we would like to fail quickly and refactor. But techniques which we're talking about here, meaning applying loosely coupled code, will definitely help us not making big mistakes and quickly iterate if you have to, so that we won't pay a huge tax in the end sometimes. So if you take a look into what is a good design, I consider a good design flexible, because nothing is certain in software development except of bugs. We always have bugs. We can't test everything. There's no way we will do that. So we'll always have stakeholders. Even if we write the code for us, we will be the stakeholder for it. So, we will have to test it. We'll have some bugs. And if we have any stakeholders, and we always have, the requirements will change, because nothing is certain upfront. And that's called Franklin rule, which means that the flexible design will be able to easily allow changes. It won't be coupled in the other sense. Scalable. Design has to be scalable, because it has to be easy to extend, maintain, and reuse. And we're talking here about the scale, and like Google scale, Bloomberg scale, not really 100 lines of code scale. That doesn't really matter. We can pull it through with simple scripting in Python, for that matter, right? But if we talk about 100 million lines of code, if we don't approach it with the software engineering mindset, we won't get far, and we'll pay the tax constantly, and we'll be so big at some point with the legacy code that we won't be able to do anything, because estimates for everything will be so huge that we won't be able to deliver anything. So we have to be scalable and testable. If you don't test our software, our users will. So let's honestly focus on that, because without that, there's no point of releasing anything, because the code which is not tested cannot be liked. Because I don't know whether you know the Beyoncé rule, but it's quite often used, especially in Google. I think Google actually invented that rule. So if you like it, you should have put a test on it. Meaning, if you like your code, and you obviously like your code, I like my code always. So who likes the code? I would assume, for the record, everyone. But if you like it, you should put a test on it because others may not like it as much if it doesn't work. So let's take a look into loose coupling right now. So hopefully the design which I'm trying to make a point of makes sense. Let's take a look into loose coupling right now. This code will be about examples which will try to refactor the hard code, which is not easy to change, into easier to change code. So I assume you probably know the rule, KISS, keep it simple, stupid. It's often used in the software design. So if you have a talk here, and we have a run function, notice here that we have a premature optimization with the always inline. Why? Because we cannot assume, don't assume that all functions, by being always inline, because that's the rule, a policy in our company, will be always better. That's not true. I would actually argue that regarding the performance, that often would be actually much worse. On the other hand, we'll have the code, which is, I don't know, how many attendees have seen code like that? I would assume everyone, because it's very often the code which is being written. Unfortunately, it's really bad. Why? So notice here that we have a manager, which is a singleton. When we start from naming, what does that mean? What is the responsibility of that? Manager? I don't know. It's like manage things. It's a singletons because we have this instance. It's a global variable that makes it really hard to test. Because how you fake it? It's coupled, really coupled to the code which we have here, because if you want to test the talk, we cannot really fake the manager instance. We would have to do like some linking tricks. Everything seems too difficult. If you applied DDD, you definitely wouldn't write code like that. And then, we get speakers, what kind of speaker we get in, all of that seems to be coupled. And after that, we get the attendees the same way. It's kind of a duplication, same access pattern. And that's the flow. But the point here is that, keep it simple, stupid. In that case, doesn't make the cut, because we made the code really hard to actually decouple, because it's constantly coupled to these singletons. It's premature. Optimization is applied by always inline. The naming is really bad because we don't have the proper abstractions here. So is it flexible? We'll take a look into our design goals. Well, it's tightly coupled, so I would say no. Is it scalable? It's really hard to extend, right? It's like we cannot easily add speakers, attendees, nothing, because it's coupled. Is it testable? Definitely not. Singletons, I think, are the hardest thing to test. Although singletons have their place. It's not like singletons as a point of having just one instance of something. It's not wrong on its own. If it's applied inside your business logic, where we actually have an access pattern to create object, because instance will create an object if it's not created, let's say. That's the really bad, lacking separation of concerns. Injecting, on the other hand, an object which is created as singleton, that's totally fine. So, what's the problems with this pattern? It's a singleton, it has tight coupling, it's untestable, it has premature optimization. I guess you can imagine where that's going. It has bad naming, and it has duplication. So the solid rules. There's also, let's call it stupid rules, where we don't want to apply things like that. So we want to avoid all of that. Software engineer wouldn't write code like that. Maybe a coder would, but we don't have coders here. We have software engineers. So one thing which is often seen in the code, and I guess everyone has seen that, is that this dot pattern. We have object 1, dot object 2, dot object 3, dot object 4, dot, 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 dot. In that case, we had the manager, instance, get speakers, get, And you can, imagine the following. And, if you've seen code like that, as a software engineer, already would notice that this code is smelly. And it's smelly because it's hard to test, it's coupled. It seems like we have wrong dependencies injected into it. But stay tuned, we'll take a look why it's really bad. And actually there's even law about it. Writing this code is breaking the law. So you can say to your coworkers, acquaintances, that if they write code like that, they're breaking the law. They may go to coding jail. So yeah, Law of Demeter, important principle, which says only talk to your immediate friends. On the other hand, that would be don't chain method calls in that particular example by having a lot of dots. You would like to have just one dot, meaning you inject a speaker here, and when you don't have to do get speakers, get manager, nothing like that. You don't want to inject manager, or in that case, don't even inject anything. That would be really hard to test. That makes the code really coupled. It's not about having a singleton. It's about that having it in the business logic means that we have the lack of separation of business logic and creation, and we coupled ourselves. And when we have the wrong thing in the first place, because we start from the manager instead of the speaker, which we actually want. I don't care how the speaker is created and where it's coming from. I just want the speaker. That's the main principle here. So this code is slightly coupled. I argue that it's impossible to test. Basically, it's really hard. Extending it's hard. But there are exceptions to the rule, as always. It's not because of C++. It's because of software engineering. Method chaining, sometimes it's okay. So if you use ranges, for example, with the pipe, imagine the pipe is the dot, different syntax, but the same principle. In that case, that's okay, because we don't change anything. Here we don't. We can apply the rule for method chaining. So we have a view, we do the drop, we do the stride. Here we don't really need to get something from the view. We just slice it differently. So this pattern is okay, but getting objects in order to access them, although we could have the stride wave in that case, if that, for example, was the speaker, that would be a different thing. But here we just have the view, which we'll try to isolate into something smaller pieces, and that's okay. So how to fix it? So I know the C++ community is really smart, and C++ is so powerful and so flexible. There are tons of ways of fixing it. So what is not a fix? The rule is talking about the dots. In Java, you have dots, you don't have arrows. So not a fix would be to change it to arrows and pointers. I would argue that's even worse, because we will have the ownership issues. Who knows whose responsibility to delete the speaker, for example. Also, which is not a fix, is to just split it. Like this code looks nicer, right? We have a manager, speaker, and we do, dot, one line, one dot per line. Yeah, in that case. Well, that's also not a fix. Why? Because, it's the same thing. It's the same thing. The principle here, which we actually want, is that the speaker has been injected, because that's only what we care about here. So we don't care about the manager. It's like when we have the talk class, manager is irrelevant to us, because we only care about the speaker and the attendees. So that's not the fix. So how to fix it? There are different ways of fixing it. In object-oriented world, which we kind of hinted here, would be to apply solid principles, which we'll take a look into. Also, I would argue that we would have never written code like that if we applied test-driven or behavior-driven development. Because why would we? That would make our life really hard when starting from test to make it impossible to test. Like, we would make a test harness which is linking based from scratch. I would argue that wouldn't be the case. But yeah, if you didn't test it and we let it slide and we start coding, we were coders, not software engineers, we would get to a point where it's, okay, right now let's test it. Because the functionality is there, we're happy with our code. We didn't like it because we didn't test it, but we are happy with it. And then we get into the point where, okay, this code cannot be tested easily, but it can be tested by making some magic or end-to-end test where we just test from the input to the output and characterization tests, system tests kind of style where we don't care about the internals. That's fine. That's fine for the refactoring where we want to refactor it, but it's bad because if something doesn't work, it's extremely hard to figure it out. That's why we have unit testing for the documentation purposes, usage purposes, and to actually find out the corner cases and find out the issues easily. Because with the integration test, we would never be able to trigger this corner case from this class. That's basically impossible. We wouldn't be able to test all the corner cases because that would probably last forever in testing, and it would be really difficult to get to that point because it depends on the 50 other states to get to that point, and we would just probably test the happy path, which is bad because users don't care about the happy path. Happy path has to work. Everything else is what is important. So let's take a look into this comparison. We were talking about this stupid approach, which software engineers don't do. Good software engineers would consider a solid principle if they applied object-oriented design. In that case, they would apply singular responsibility, which we'll talk about, and other patterns, which we won't talk about, but are also really important. They would also apply dependency inversion, dependency injection, and they would avoid all the things on the right here, because all of them are just stupid. So we don't want to be stupid when we're writing the code. We want to be smart. Not cleverly smart, just software engineering smart. So let's fix it. There are ways to fix it. I would argue that there are ways to fix it. In my experience, we can do it. So since we are software engineers, we know about single responsibility principle. I bet all audiences around the globe know about it and know what is the Swiss knife, which is exactly what the manager was. The manager had probably, it's called often a God object, all the abilities to do everything, literally everything. Scissors, knife, everything else. So just because you can, doesn't mean you should. Very important rule. A class should have only one reason to change. Manager is a bad name because when we cannot put a name on it, meaning it has too much responsibilities. If we have something which has simple one responsibility, you can always go too far. Often functional programming might be going sometimes too far because you have just only one function per interface, right? Because it's functional programming. Sometimes you may want to have more, so we can argue here. I love functional programming, so I won't put it down, but one can argue that that's going too far. So if you just have, so imagine that you have just interfaces with one function, always. Definitely have one responsibility then, right? But maybe you sometimes want to go a bit further, because if you go too far, that's not too good either. So what is important? ETC, easier to change. That's what we always want to keep in mind when we write software. Would that decision we are going to make right now make the code easier to change in the future? If the product owner will come to us and say, Kris, all the requirements you were working so hard are going to change next sprint, how you will react to that? I didn't even test it yet. I just started, to write my singletons. Well, sorry, that won't be a situation I would like to be in. And as a software engineer, I would like to be in that situation where it's like, no issues. I everything I have written, I can easily refactor. It's already tested. I release the small pieces. I can easily change the stuff so that you can, shoot whatever you want at me, and I won't be, staying over hours in order to accomplish that. I will probably speed it up. Okay, so how the single responsibility would look in our talk example. We have a speaker, responsibility gives a talk. Hopefully a good one in that case. But yeah, just pointing out here that single responsibility doesn't mean not tightly coupled. As example here, the name is coupled, but the responsibility is there. The responsibility is to talk. So that's just one. We have one function, definitely one responsibility. Responsibility of attendees is to ask questions. So I'm looking at the Discord. There are no questions. So the goal not fulfilled at the moment. So that's still tightly coupled code because we have names coupled to attendees. But I think you get the gist. Sorry about this ACCU attack. That's not the one which are at the moment. So, and notice here that we have the speaker still tightly coupled, attendees tightly coupled because we have names inside, but we have the talk, which has the run call. And all of that seems a bit better, right? It's like we have smaller classes, smaller pieces. So I would say that's an improvement over the oversimplified, keep it simple approach which we start from. We don't have singletons, we don't have managers. We can test it, potentially, by, sort of, because it's kindly coupled to data. Excuse me. Still, so we might have some problems, but that's the first step. So is it flexible? It's better, but it's still coupled. Is it scalable? It's more etc than before, so that's good. Is it testable? It's hard to put fakes on it, right? It's hard to change the speakers. Kris is always the speaker. I bet no one would like that in the long term. So we don't want to just couple our options. Because as I pointed out, the product owner comes and says, no, this is a new feature. Like, we have to support different speakers. And that wasn't the case before, but we coupled ourselves to just one speaker, and right now we regret that. So yeah, let's consider classes to have only one reason to change. But still coupled, right? So let's move on. Another approach on top of single responsibility is to apply dependency injection. I love dependency injection. I spent a lot of years writing a library for it. So it's great. In my opinion, it's great, but it's only great in the large scale development. It won't help for, I would say, coders, like, it's often a quote, sometimes bedroom programmers or something like that, where you like hundreds of lines of code and like when dependency injection, especially automatic dependency injection, doesn't really matter, especially if you don't write tests. But what is it? It's often, this mysterious term which a lot of coders are scared of. From the design perspective, dependency injection is a way to reduce coupling. It's all about the coupling, right? We want to reduce it. Dependency injection is just a form of doing it. In C++, a simplified version of dependency injection is, I have a constructors. If I have a constructor, I probably applied some sort of dependency injection. So we're not coupled anymore, that have the members inside initialized in place. We inject them. And right now, that doesn't mean that everything is fine and dandy because we have constructors. Like, what we put into those constructors makes the whole difference. We can totally screw it up, even with the automatic dependency injection. You probably maybe heard about software service locator pattern. When we propagate the injector, that's really bad design choices. But we'll take a look into them, so stay tuned. Don't sleep yet. So, as I pointed out, whether DI is done depends on what and how we'll pass into the constructors. And really important because I often get that question since I'm an author of a dependency injection library. DI, the automatic DI doesn't imply using a library. Not at all. Manual dependency injection is a totally valid way of testing and writing software. DI libraries may help, especially in the long term, because they allow by reducing the wiring, which we'll take a look at some point. So, the order of constructor parameters won't matter, whether we change something from smart pointer, like shared pointers to unique pointer, doesn't matter, ownership and everything will be maintained. So as a software engineer, I want to focus on high quality code, the business logic, the algorithm. That's where I want to spend my time of the design and things. I don't want to spend time of, putting classes together because I've gone into, these solid principles. And right now, like, it's hard because I'm wasting time writing unit tests. I have all this wiring. It's difficult. So in the large scale, that may help. So let's take a look. Tight coupling. As we had before, everything is still tightly coupled. So that's what we've seen. Nothing has changed. Less coupling. As you can imagine, dependency injection, voila, that's it. It's all about the constructor. So we have a speaker and we inject the name here into the speaker. So speaker is not coupled anymore to the name. And that's, very simplified example, but you can imagine that before, the choice was made for us. Here, the choice is on a different side. And the same here. We have the talk, CppOnSea talk, which we have the speaker and attendees being injected into it. It's often called the Hollywood principle. Don't call us, we'll call you. So what we'll inject is important. But that doesn't make it as simple as you may think it is. Because there are tons of gotchas. What we'll inject through that constructors really make the difference. So let's take a look into what kind of issues we can encounter while it's doing so. So for example, not using constructor consistently. We have the attendees injected with names, but speaker, although it has the name to be injected into it, we inject it inside the CppOnSea talk. Sorry about that. So notice here that that's wrong. We don't want to do that. And actually, the solution, and a lot of coders, not attendees here, would think that the solution would be to inject the name into a CCU talk and propagate it to the speaker. That actually would be a leaky abstraction, which we'll take a look into as well, and that's actually a bad solution. The solution is to inject the speaker into the talk. So coupling the name, even if it's exposed to us on the other side, it's bad. Injecting the type, it's better here. Using singletons is as bad. We pointed that many times. So I just wanted to clarify. Try to avoid singletons, but it's okay to inject them via constructor. Singletons still have its place. It's just not mix them with the business logic. It's part of the creation stuff, so it should be in the wiring and then injected into it. So that we can write unit tests. We don't have to deal with the singletons. We can just inject an object. So when we see instance, that's usually bad. We should avoid that. As pointed out before, when you have this name being injected through the talk, that would be a leaky abstraction. Why? Because we propagate something which we don't care. The talk doesn't care about the name. So why we want to inject the name into the talk? We want to inject the speaker, because that's what the talk cares about, because it will call speaker.talk. If we inject the name, we propagate the name into the speaker, and that's a leaky abstraction because we don't care about it. And this pattern is often used with the CRTP. When we inherit from the base, with the drive, blah, blah, doesn't really matter. But the fact is that we have this constructor which takes args, and when we propagate some parameters somewhere and some others somewhere else. I bet you've seen code like that. That's really bad design. It's smelly immediately, and it should be avoided. We should inject the things which we care about, meaning we use directly, like with one dot, Law of Demeter. This code is hard to change. It's not etc. Because if we change the speaker constructor, we have to change the talk constructor because we have to propagate those parameters. If you have attendees as well, and that will change, we have the talk yet again a change. But that's bad. So instead of passing the name, let's pass the objects which are already constructed. So that's good. Passing the names is bad. So inheritance is the base class of evil. If you seen Sean parent talk, which I really encourage you to see if you haven't. Software engineers definitely seen it. You don't want to do that because that's as an outcome with CRTP, but it's as bad as the other approach. It's even worse because we expose potentially by public inheritance here, even the API of speaker, we may get into the problem that we have the same functions from multiple bases. Just bad. Let's not do that. So let's prefer composition over inheritance, and I really encourage you to see the talks about it, especially Sean Parent's talk. I think the good one. So let's not inheritance from anything very often. It's hardly ever, the base is usually a bad design, I would say. So because of the reasons provided, inheritance just makes things harder. Composition is just easier. And especially don't inherit from like STL containers or something like that to extend them. That's really bad. There will be a lot of subtle issues which we can encounter afterwards, so we want to avoid that. One of the important rules which we're talking about is to talk to your immediate friends only, right? So that's the law of Demeter. So here, notice that it's often sometimes a service locator pattern as well. So we inject the manager. Like if you see that, immediately take a look. I wouldn't accept this, review at all. Manager, I don't know. It's a talk manager, okay? That's not solving the issue. Because notice that we get the speakers, get Kris out of that. That's, again, the coupling. We want to inject the speaker. And that's why I'm showing so many examples here, because that makes the whole difference. Unit testing of that is difficult. Speaker can be easily tested, right? With data, we just inject the name, and we, verify that, different speaker talks. That's fine. But here, we have this manager, and how we test this talk? We have to create the manager. We have to fake the get speakers call. Then we have to fake the get call, and then return a speaker out of it. Why we would do that? It's like if you apply TDD, for example, we would never write that. But that's often the case. So avoid that. Let's only talk to our immediate friends. Not in real life, but yeah, in code, software engineers don't talk to distant friends. Coders might do, but software engineers don't. So inject the speaker here, because that will, if you have multiple dots, meaning the design will be smelly and hard, and will be tightly coupled and hard to test. And in 10 years times, that will be difficult because, the more requirements will come, we'll have the more get speakers, get attendees, get, I don't know, anything else. And there'll be more and more of that because, the code grows. And, don't copy paste the stuff, just refactor that, because in 10 years time, I bet that won't be maintainable at all. And we will get to the point where all estimates will be so high that we might be able to deliver anything. Yeah, so that's Law of Demeter. Don't break the law. Now using strong types. So imagine here that we have a weak API. We get the name and the last name. Both of them are strings. And what's wrong with that? It's like they're just strings or string views or whatever, right? That's fine. Well, that's okay. Well, we don't have named parameters in C++, right? So if we, by mistake, put the last name first, that's fine, right? But no, that's not fine. That shouldn't compile. That's the weak API, which makes the code hard, like easy to make subtle mistakes, which might be hard to find. So we can apply strong types. C++ doesn't have native support, which I would say suck, but you can, with C++20, with the NTTP stuff and the fixed string kind of approach, we can make some named parameters out of it. And in that case, when you have the name, first name and last name being the strong types, we kind of imitate the named parameters with the proper types. They're not convertible to each other. So if you misspell the order, that would be bad and it won't compile. And that's what we want. We prefer compilation errors over runtime errors anytime. And there are a lot of different ways of applying that in C++. I bet you have your favorites. And there's inheritance, which is with the virtual polymorphism, dynamic dispatch, with the virtual classes, when rank is equals 0, with the virtual kind of opaque method, often still used in the object-oriented design, but it has its drawbacks. It's kind of slow. It's hard to get the virtualization of them, and it's not ideal. And it requires this interface which has to be inherited, and we know that inheritance is bad in principle. Better approach, which is, for example, used like in type trace in Rust, is to apply type erasure. So in that case, we don't have the inheritance anymore, but we still have the same flexibility. It's still type erased things, so there's some sometimes heap allocation depending on the small buffer optimization, and there's a function pointer, so there will be some performance overhead on top of that, but it's still better because, for example, we can have a container of type erased things we can store into and then use it if you care about the runtime. From C++17, we can do other things, std variant, std any, that's options that you have. Variant, the main problem with it is that it's closed, so the set number of types is closed. So we cannot, easily test our fake because we use the variant, which we say, regular speaker, awesome speaker, and stuff like that. And we don't say fake speaker in the production, right? Because that would be weird. We don't want to test code being in the production. std any is another approach. It's just slow, and we have to know how to cast it. Sometimes it's a combination of both, which, is the solution when you have a variant of closed types plus std any for testing. But that makes the code even more difficult. So there are use cases for it, but mainly in the implementation of details on the API provided to the users. Templates, full X templates. For the record, I don't know. I like templates. TMP, template metaprogramming, is awesome. It's this cool feature in C++, which should never happen that way, but it did, and it enables a lot of use cases, and it allows us to write and generate code as well. Generic in a sense, different types. However, it has its drawbacks because it wasn't designed to do that. So it's hard to get the error messages up front on the point of instantiation side. We always get it from, the library code, which we don't want. So C++20 introduces concepts which we can limit the issues here. So that's a bit better. And there are obviously tons of other ways like functional programming and combinations of any of those to make things even better. As I pointed out before, inheritance is the base class of evil, so we don't want to talk about this one. Functional programming. If you haven't seen this talk, I really encourage you to see it. It's a talk from Scott about functional programming design patterns. So, you notice here that I was talking about object-oriented a lot because that's often used in, software engineering work, but functional equivalents are as good and sometimes even better because, from teaching perspective, all the design patterns in functional programs are very simple. It's just a function, right? It's just how you apply it, how you carry it. All of that is how to bind it very easy. In object-oriented words, you have to learn the patterns to apply it. Okay. Yet another talk which I wanted to mention here, if you write code like I do on a daily basis, which is a lot of templates, a lot of, reflection, a lot of template metaprogramming, you would like probably to know about design by introspection. Design by introspection is an invention of Andrei Alexandrescu, which allows you to combine compile time predicates in place to get different behavior. So it's often used in C++20 that we write if constExpr requires something and then we do something like that. It's better than just an if because it doesn't have to compile if you provide something which doesn't satisfy that requirement. So that's pretty cool, and we can do that in C++20. Design by introspection has more properties, but not all of them we can do in C++ at the moment, but this one we can, and it's quite neat. So instead of propagating virtual interfaces, we can just propagate types, apply policy design, design by introspection, and get the behavior we want. So, depending on our needs and project, we should apply different abstractions. So, I'm working for a high-frequency trading company. Performance is really critical there. We apply a lot of templates and concepts on a daily basis. Doesn't mean we cannot be software engineers. It's harder because, there are a lot of magic related to templates, but doesn't mean that we cannot write code which in 10 years' time won't be maintainable anymore or understood. So if you know everything at compile time, or we can't predict what kind of limits we have, and it's mainly the case because even if we have runtime options, there are, set number of them, we can predict and compile them in upfront, just pick at runtime, the compile time options which we compile in. So that's one approach of doing that. If we really have to stick with the type erasure, runtime dependencies, type erasure would be the case for me. That's the way I would go. Because mainly it doesn't require the inheritance. Where is the use case for inheritance? I think these days, basically never. I don't honestly see a use case for virtual dispatch these days. Besides maybe easily mocking or something like that, but difficult to find it. So just to wrap it up, template and concept, I would say, are the best solution if you care about the performance. Type erasure, otherwise if you want to be more flexible, that's the way I would go about it. So how we would write that? So in case of C++20, we would write the concept here, speaker. Speaker has to talk, so that's the function. You have the requirement. You've probably seen the coding examples of that, and it returns a void. And that's the concept for it. So then we have regular speaker, not the keynote speaker, not the awesome speaker, just the speaker, which without inheritance take the first and last name. Notice here we didn't apply one of the rules. I will let you pause and figure out which one would be even better. But the main principle and fact is the fact that we don't have inheritance here, so that's good. We have something which has to satisfy the concept, meaning that it has to be the talk function, but that's it. And then we have this CppOnSea talk, where we propagate the speaker and the attendees as the template parameters in that case. Notice here that instead of typing class struct, we just pass the concept. So speaker and T-speaker, attendees. So the speaker, the first part of it is always the concept. So with the concepts, we propagate them. And notice here we inject the speaker and the attendees into the talk itself by propagating them accordingly. So all of that is great. We have what we actually wanted. So right now we'll just quickly describe the wiring because we have just a few minutes. That's where a lot of problems come about. That's where the DI approach can fix it because we have to introduce all these objects. But that's good because that's on the user side. We don't have to care about it ourselves. Our APIs are not coupled to it. So wiring is the separation of the logic from the business logic, meaning we don't have new, make unique, make shared in our code ever. That's only in the wiring side, which is related to the composition route. So if you apply software engineering techniques and you are a software engineer, you would have a main, which is short, and where the whole wiring is happening. So just to sum up the dependency inversion principle, is it flexible? Yes, loosely coupled. Is it scalable? Easy to change? Apply is definitely testable. Yes, we can inject fakes, stubs, mocks as we want. Can we go too far? Can we go too far? Yes, I pointed out before that we can go too far to have too many classes, too small classes. Just, you have to find a balance. And you have to always ask yourself the question, is that ETC easier to change for the future? Is that good for employees? And is that good for me? Will I have to stay after hours if I do that this way? And, don't try to outsmart, the code. You, as a software engineer, you know better. So, if you have the speaker, that would be an example of the same responsibility for the speaker, but two different interfaces. There's no need for that. That would be going too far. Aiming for 100% coverage, just the sake for the coverage, is always going too far. We don't want to do that. That doesn't make much sense just for the sake of doing that. Having 80% coverage where you cover all the cases which are reasonable to cover makes a lot of sense. And if you just apply DD, you will just get it. So going too far is a risk. It's okay. So doing that, we have to always think about ETC. ETC to the rescue, meaning easier to change code, design is the way to go. So the last thing, because we have just 3 minutes, is BDD. So here we have the behavior-driven development test, which we will be able to apply the behavior from our implementation, given one then. And that semantics really makes it easy to develop acceptance criteria if you get it from the product owner. And if you apply BDD, we'll get loosely coupled code out of the box because we have to put the mocks, stubs, it will drives, easy to change code, and definitely it will be testable for us. So always consider test driving your code. And the difference between BDD and TDD, just for software engineers, BDD uses automated examples to guide us towards building the right thing, and TDD uses unit testing to guide us towards building it right. So that's the difference between those. So just to sum up, good practices are good practices for a reason. It's not what I invented. I'm just trying to apply it. I'm just trying to share it because I care about the quality of the code around the world. And hopefully you do as well, because software engineers care about that, because it's all about going fast. And going fast implies going well. So it is better than being stupid. Law of Demeter is an important part of the loosely coupled code to make it easier to test. TDD, preferable, single responsible dependency injection. If you apply those techniques, we definitely will go far. We'll be able to easily change the requirements as they go. DI can be easily misused. As we pointed out, it depends what you pass by the constructor, and it doesn't require a library or a framework. That's also an important part of the talk. So yeah, let's not only talk to our immediate friends, and with that, it's time for questions or time for finish the talk. If you enjoyed it, and hopefully you did, thank you very much, and I hope we'll have more software engineers and we'll improve the code around the globe. So thank you.